We are used to seeing chatbots type out answers with the smooth, conversational flow of a human typist. But beneath that clean interface, there is no thinking happening. There is only a massive, high-speed sequence of mathematical matrix transformations. When a language model generates a response, it is performing a process called inference. During inference, the model is not learning, adapting, or updating its knowledge. Its internal parameters are completely frozen. Inference is strictly the forward application of that frozen model. It takes an input, runs it through millions of fixed equations, and outputs a mathematical probability distribution dictating exactly what the very next piece of text should be. Today, we are going to mechanically trace the exact life cycle of a single text prompt. We will watch it convert from a simple string of English characters into a multidimensional array, or tensor, travel through a neural network, and emerge back out as generated text. Our test subject for this trace is Qwen3, specifically the 0.6 billion parameter base model. It is a highly capable open-weight language model that we can run locally on standard consumer hardware. This diagram shows the text generation pipeline's 3 stages: input preparation, the LLM pass, and output processing. Notice the massive blue LLM block. Once pre-trained weights are loaded, it becomes entirely static. No internal data changes occur inside the network during this process. Mastering this foundational, step-by-step text generation loop is the absolute prerequisite for understanding how modern AI systems are built, scaled, and optimized. What feels like a ghost in the machine on your screen is actually a highly structured, sequential data pipeline, and it is one that any engineer can trace. We begin our trace with a standard user prompt. Explain large language models. Neural networks cannot read raw alphabet characters or strings. Because they are mathematical engines, they require their inputs to be matrices of discrete numerical IDs. To translate our text, we use an algorithm called byte pair encoding, or BPE. BPE is a data compression technique that fractures words into frequent, recurring subword patterns. When we run our prompt through the Qwen3 tokenizer, it applies this algorithm, fracturing it into 6 distinct text blocks. Because explain is capitalized at the start of a sentence, the tokenizer splits it into 2 common subwords, X and plain. But the word large is kept entirely whole, and it even absorbs the blank space immediately preceding it to help the model detect word boundaries. From there, a lookup table assigns a specific integer to each block. X becomes 840. Plain becomes 20,772. These numbers are the token IDs. These IDs are drawn from the model's fixed vocabulary. Qwen3 has a vocabulary size of roughly 151,000 possible tokens, which dictates exactly how high these numbers can go. We now have a flat, one-dimensional array of 6 numbers, but PyTorch, the deep learning programming library powering this pipeline, expects data to arrive in structured 2-dimensional batches. To satisfy this architectural rule without changing the actual token data, we apply a specific PyTorch tensor operation called unsqueeze0. This operation wraps the sequence in an extra dimension, converting our flat list into a 1x6 matrix. We now have exactly one batch containing 6 tokens. Through tokenization and batching, the messy human language has been successfully converted into the precise geometric shape the neural network requires to begin computation. With the data accurately formatted, the 1x6 tensor enters the base neural network. This architectural diagram shows the tensor passing upward through a deep stack of 28 repeating transformer blocks, interacting with grouped query attention mechanisms and normalization layers along the way. But the most important event happens exactly as the data exits the final layer. The compact 1x6 input expands into a massive grid, measuring 6 by 151,936. The rows are straightforward. The 6 rows in this output matrix perfectly correspond to the 6 input tokens we originally fed into the model. The massive column count perfectly matches the total size of the model's token vocabulary. Inside this grid are hundreds of thousands of individual floating point numbers. These are the logits, the raw, unnormalized prediction scores calculated by the network. Every single column holds a distinct mathematical score, determining exactly how likely that specific vocabulary word is to logically follow the sequence. Here is the crucial mathematical insight for text generation. We do not actually need 99% of this massive matrix. Because our only goal is to predict this single next word at the very end of our sequence, only the raw scores in the very last row are relevant. The first 5 rows are simply predicting the words we already provided in the prompt. This diagram shows exactly how we use a -1 slice indexed in the code to isolate that final row vector, completely discarding the intermediate values highlighted in the dashed box. We then apply a .detach command to this isolated vector. This disconnects it from PyTorch's memory-heavy gradient tracking system, saving a massive amount of RAM since we are not training the model. In a fraction of a second, the model transforms a short text prompt into a massive probability space, only to ruthlessly discard almost all of it to isolate a single predictive vector. We are now left with one single row containing 151,936 prediction scores. To select our winning token, we use a standard mathematical function called argmax. Argmax scans the entire vector, compares every single score, and locates the absolute highest scalar value in the array. This diagram shows argmax extracting the exact index position of that highest value. In this example, the winning score is 20.5, and its index position is 20,286. That index position perfectly aligns with our vocabulary list. It is exactly the token ID for the generated word, which decodes back to the readable text string large. This brings us to the core engine of text generation, the autoregressive loop. This overview diagram illustrates the loop in action. In step 2, the newly generated token ID is physically concatenated to the original input array, extending its length from 6 integers to 7. That entire new 7-token sequence is then pushed back through the LLM from scratch. The model processes the whole chain again to predict the 8th token. This loop repeats relentlessly, growing the input sequence by exactly 1 token per cycle. It only breaks when the model explicitly predicts a highly specific stopping ID, token 1,051,643, which represents the end of text command. The fluent paragraph you read on a screen is not generated in one fluid motion. It is a mechanical, stuttering loop of evaluating the past to append exactly 1 discrete integer at a time. While this naive autoregressive loop is mathematically sound, running it exactly this way in the real world is computationally brutal. On standard consumer hardware, this unmodified loop generates text at a painfully slow rate of roughly 5 tokens per second. The bottleneck is caused by massive redundant matrix multiplications. By feeding the entire ever-growing sequence back through the model on every single pass, we force the network to recalculate the attention scores for tokens it has already thoroughly analyzed in previous iterations. With every loop, the bulk of the computational power is wasted recalculating the exact same math for the exact same historical text. To solve this inefficiency, engineers deploy an industry-standard optimization technique known as KV caching. Instead of discarding intermediate math, the system extracts the keys and values of historical tokens, storing them in a dedicated memory cache. With the past locked in memory, the old sequence bypasses heavy matrix math, and only the new token passes through the LLM. In the code, the first pass takes the full prompt to fill the cache. But all subsequent iterations only execute the model on the newly generated token, utilizing the cache to provide the necessary historical context. This specific compute for memory trade-off immediately yields a massive 5 to 6 times increase in token generation speed. Scaling large language models in production is a constant, unyielding war between processing limits and memory bandwidth. Every optimization must balance the two. Grasping this foundational text generation loop, along with its memory caching bypass, is the absolute bedrock of modern engineering. You must understand the engine before you can attempt to upgrade it with advanced techniques like reinforcement learning or distillation.